Hi everybody, good day everyone. My name is Darmawan Utomo, and on behalf of the others outdoors, I would like to thank you for giving us opportunity to present our research paper. And the title of our paper is Class G Series Audio Power Amplifier for Subwoofer. Let me list three of the other authors. The first author is Mr. Budihardja Murtianta, and the second is Atyanta Nika Rumaksari, and Jae-Wook Lee. Third. We are from Faculty of Electronics and Computer Engineering Satyawacana Christian University. And here our outline presentation that starts from introduction, method, result and discussion, and conclusion. Let's start with the first section. In this section, introduction, we will talk about audio amplifier principle, problem, and proposed solution. Principle of audio amplifier. An audio amplifier is an electronic device used to amplify the small signal here at the input into the large signal at the output. This large voltage and power level at the output would be used to drive the speaker. The problem in audio amplifier is that in the signal amplification process, there is always power or heat dissipation or power losses. The amount of heat dissipation is actually proportional to the square of the voltage difference between the source supply here and the output signal of the audio amplifier. The smaller output voltage level of the audio amplifier, for example here, will drive the greater heat dissipation, which means the efficiency of the audio amplifier is getting lower. Therefore, here to increase the efficiency of the audio amplifier, the voltage difference between the power supply and output signal at the audio amplifier output must be as small as possible. And this effort can be achieved with Class G amplifier. Here we propose a Class G audio amplifier design for subwoofer. Why subwoofer? To drive a subwoofer generally requires large power. Greater efficiency will save more energy. The specification of the design Class G audio amplifier includes a frequency response from 20 to 200 Hz, an 8 ohms output impedance with a gain of 2 and 80 watt of output power. And to test or to compare our result with the other schematic, the power efficiency of this Class G amplifier will be compared with a Class AB amplifier whose active components both work in linear region or non-switching. Here is the example of the Class AB that will be used as the comparison. Here we see there are two voltage source here. Normally this part is for positive cycle and the below is for negative cycle. In this section, we would like to present block diagram and also the description how the proposed system can achieve the goal. In here, two voltage sources of class G amplifier are employed here, namely high voltage and low voltage. So here we have a high voltage block and low voltage block. If the output voltage level at the amplifier is low or below the reference voltage level, the active voltage source is the low voltage. So this one is the output of the power amplifier. So if we compare our output here with voltage reference, here for example this one is too low, lower than the voltage reference, then we should use the low voltage source here. Conversely, if the output voltage level here, output voltage level is higher than the reference voltage level, then the active power supply voltage source is the high voltage. So if this output voltage level is higher than this one, and we need to activate the high voltage level source. To find out whether the output voltage level is greater or less than the reference voltage level, a voltage comparator is used. The function of this comparator is to compare the output signal level with the reference voltage level. So this one is used to compare the voltage reference and the output voltage level. And the comparator will trigger the electronic switch. That is, if the output signal level is greater than reference level. Then the electronic switch will link the power supply to high voltage power supply voltage source and vice versa, so that the power supply is adjusted to the suitable power supply. If the input voltage level of amplifier is small after being amplified, the output voltage level is also small or less than the voltage reference here, and uses power supply voltage that is also small here than the voltage reference, and so that the power dissipation is relatively small. If the amplifier input voltage level is large after being amplified, so after this become large power supply here, the output voltage level is also large, right? And the system employs a large power supply voltage so that the power dissipation can be conditioned to be relatively small. Why should the supply voltage be increased? It is because the amplifier supply voltage must be greater than the amplifier output signal, so that the output signal is not clipped or deformed. Therefore, the power supply voltage must be set greater if the output signal is increased. In this section, we would like to explain and discuss the schematics and waveforms results, some measurement points, DC input sweep, and total harmonic distortion and frequency response. Let us see the schematic first. There are pairs of components such as high and low voltage sources. We have high voltage sources and low voltage sources. And then voltage reference here, comparators, and electronic switch. The above component are positive cycle and the below is for negative cycle. Here we set the input with sine wave of 26 peak to peak. and or we can say 30 volt voltage peak with 1 kilohertz frequency. After amplifying with gain equals to 2, the output signal has here, the output signal have 52 peak to peak or 26 volt peak as shown in the waveform in red. So we can see here in the red. Waveform blue represent the supply condition for the amplifier. Yeah. This one is for low voltage and this one is for high voltage. When the output voltage reaches the reference voltage, here for example, the high voltage source is activated here and vice versa. So if this one is below and then going to low here. This shows the location means this orange triangle show the location where the low voltage source is switched to high voltage source or vice versa here. Next, we will discuss some measurement points as in the table 1. Table 1 show the results of several conducted experiments. The first column here is the voltage output signal. The second column is the power output. And then this block is for the result from class G. And the second block is for class AP. The total power that derived from the supply can be calculated and referred as a PVA here. PVA actually is just the sum of the low voltage supply and the high voltage supply source here. We just add this one and we can get this result. This one is the total power that drawn from the supply. And then the next column is the dissipation in the transistor. And then how to calculate the efficiency. For class G, we need to calculate, I think it's almost the same here, power output. And then we divide it with PVA1 plus PVA2, or we just call it PO over PVA, then multiply with 100%. On the same way with class B, where we divide the power output with the PVA in class B, so we can get the efficiency ratio. For when in the condition V output less than 18 volt, as we designed that 18 volt is our threshold as a voltage reference, the PVA2 is still deactivated. So we can see here, if our voltage peak is less than 18, and then PVA2 is always 0, because this means that the high voltage source is always deactivated. So as in column PV2, the class G will always deactivate the high voltage when the signal is less than its reference voltage. In this case, our reference voltage is 18 volts. In other words, the power is only drawn from the low voltage source, which is close to the output voltage. Therefore, the efficiency of class G is always greater than or better than the class AB, which always maintain the high voltage source. So in this case, class AB always maintain the high voltage source. We also conducted the second experiment here. The previous experiments set the sine wave as input. And here we also conduct the DC sweep simulation to show the broad area where the class G outperform or is like a class AP. The design amplifier has gain twice with a power supply limit of 40 volt. Hence, DC sweep is regulated from -20 to 20 volt. So this one is the DC input switch from -20 volt to 20 volt. And for the alternate is the power that is drawn from the power supply. We have two classes here. The first classes is class AB and the second classes is for class G. So the linear part here is class AB, and this linear part but lower than class AB is class G, and then after the threshold of the reference voltage it becomes almost similar. The class G and class AB utilize 4 and 2 power supply sources respectively. The class G designed to have positive and negative power supply, each having 2 power supplies, and in the class AB only 2 power supplies are required. The total value of positive and negative power in class G is compared with class AB here, right? We will compare from this graph. This figure displays the output power of class G and class AB as a function of DC sweep. The gray area is the area where class G outperform or wins than class AB. As we can see here, the power drawn from the class AB is larger than class G. Based on the ratio of the gray area to area under class AB during the DC sweep experiment from -9 to +9, so this one from -9 to 9 volts, and from -18.5, here the linear version, to the 18.5 volts, it is shown that our proposed class G yields 43.8% higher efficiency than class AB, but only 10.4% more efficient than class AB. We also conducted the other experiments to measure the total harmonic distortion of the output signal. Both our proposed class G and class AB obtain total harmonic distortion less than 1%, which is included as a high fidelity. And we also conducted the third experiment. We try to know the frequency response of the amplifier, which is measured from 20 Hz to 1 kHz with the same input amplitude. The result of measuring the frequency response shows a flat response for the frequency range 20 to 200 Hz. Thus, this amplifier qualified as a subwoofer power amplifier which has a frequency range of 20 to 200 Hz. Conclusion: we have already designed a class G power amplifier for subwoofer, meets the specification including here, and the power efficiency of our class G amplifier is greater than class AB. The efficiency difference between the two amplifiers becomes larger as it approaches the reference voltage of the comparator circuit and comes smaller as both outputs approach the highest output voltage. This design can be developed more efficiently by increasing the number of voltage rails. And also varying rail voltage is useful for minimizing the difference between the voltage supply level and output voltage level. This is conclude with our presentation. Thank you very much on behalf of me and the other authors. Bye bye.